we came across the concept of a Fermi energy and we calculated this Fermi energy, and it turns out that these Fermi energies, because of quantum mechanics, these Fermi energies are really high. They are not determined by the temperature of the solid, but they are rather determined by the density of electrons, the number density of electrons which are present inside the material. The Fermi energies and the Fermi velocities turn out to be very high inside the solid. Next, we come across a concept which is the density of states. It is a related concept which will be useful as we go along in this course. So, I will like to introduce it right here itself. If you recall, how did we count the total number of particles in the solid? The total number of particles is 2, which comes from each state in the system being occupied by 2 electrons. K is the state, the individual states, and Fd is the Fermi-Dirac distribution, which is equal to 1 for energies which are less than the Fermi energy, and it is equal to 0 at energies which are greater than the Fermi energy, where the chemical potential is at 0 temperature is equal to the Fermi energy. And the summation, if we write it as an integral, and d cube k is the volume element in this momentum space. So, d cube k is the volume element. So, let us relook at this expression a little closely. So, n is equal to 2 into V by 2 pi cube integral d cube k, integral over the volume element inside the system, inside the in the momentum space, and Fd is the Fermi-Dirac distribution minus Ef. Okay. For energies less than Ef it is 1, for energies greater than Ef it is 0, and this we can rewrite it as then for a sample of given volume, this is the volume of the sample, for a volume of the sample of size V, the integral is this quantity into the occupancy of the state, which is governed by the Fermi-Dirac distribution, or the total number of particles for a sample or for a material of volume V and let me call this as Gk. Okay. If I write it as Gk dk, then for a material of volume V, the total number of particles is V into integral Gk into F d Ek minus Ef dk. I will rewrite it slightly as we go along. Okay, but now we are defining something which is this 2 into the volume element over 2 pi cube. So, this is Gk dk is 2 into this volume element in the momentum space divided by 2 pi cube. Let us look at this a little bit more closely to give it an interpretation. What is this thing which is Gk dk which is coming into the picture? So, as I had said that for a metal, in your momentum space you can define a volume element. Okay. There are integral states which are available, there are integral set of states which are available in your momentum space. All over the momentum space they are distributed. There are states which are available in this momentum space, and d cube k is a volume element that you are looking at in the momentum space. So, we define the volume element as 4 pi k square dk, namely it is a shell of a sphere. A sphere has surface area 4 pi k square. In the momentum space, a sphere has a surface area 4 pi k square. If you consider from the origin a sphere, okay, then the sphere will have a surface area of 4 pi k square, and if you consider a thin shell of width dk, then the volume of this shell, the volume of the shell is 4 pi k square dk, which is basically your volume element. The volume element we are considering is spherically symmetric, and we are considering what is this volume element in this spherical shell around the origin. Origin has the 0 momentum state, and we are looking at a volume element. So, it does not depend on the theta and neither does it depend on phi. The volume element is just depends on the k vector. We are considering it as a spherically symmetric shell. Okay. So, there is no theta dependence of this volume element, as well as we have integrated out the phi dependence, and that is why you will have 4 pi k square dk. And it is very easy to see that if you integrate this d cube k, which is equal to integral of 4 pi k square dk 0 to k, integrate it over 0 to k, there is no theta or phi dependence. So, we have gone into the spherical coordinate system and we are defining the volume element. There is no phi or theta dependence, and this will give you a volume element which is 4 pi k square dk. If you just integrate this, this is nothing else but 4 pi by 3 k cube, which is the total volume of the sphere. Okay. So, you are allowed to write your volume element provided there is no theta and phi dependence, and there is no reason to believe that in a metal you will have some angular theta and phi, namely there is some asymmetry in the momentums along x, y and z direction. We remove those complications and we consider an isotropic momentum distribution, and for this isotropic momentum distribution we consider this spherically symmetric shell whose volume is 4 pi k square dk. The volume of the shell is 4 pi k square dk. The number of states between k and k plus dk whose volume is k 4 pi k square dk is 4 pi k square dk divided by the smallest volume element which each state can occupy, which is 2 pi by L, and 2 is the number of states which are available for occupying plus minus 8. So, you have this factor 2. So, you will get 2 into V 4 pi k square dk divided by 2 pi the whole cube, or the number of states per unit volume number of states per unit volume V of the metal or the sample between K and K plus dk is nothing else but 2 into 4 pi k square dk divided by 2 pi the whole cube, which is our term d cube k by 2 pi the whole cube. The volume element, we have just replaced it with a spherically symmetric volume element because there is no momentum distribution along the x, y and z directions. There is no asymmetry in the momentum distributions in the x, y and z direction. So, the simplest case to consider is a uniform momentum distribution along the x, y and z direction. So, we consider the volume element d cube a k is basically a volume of a spherically symmetric shell. So, the number of states which are available between k and momentum k plus dk is the volume of this shell, which is 4 pi k square dk, divided by the minimum volume that you have. So, the number of states per unit volume of the sample between k and k plus dk is this, and this is called the density of states into dk. Okay. The number of states per unit volume between k and k plus dk. So, the number of states between k and k plus dk is written as density of states into dk. This is g of k dk. So, g of k dk is 2 into the number of states, this is all per unit volume, gk dk is 4 pi k square dk divided by 2 pi the whole cube. Okay. And so, the density of states, this is the density of states, which measures what is the density of states that are available in the system. Okay. That density per unit volume that we are calculating is this, which is 2 into 4 pi k square by 2 pi cube. This is nothing else but, if you recall, d cube k by 2 pi the whole cube, okay, and n, which was written as integral of d cube k divided by 2 pi the whole cube into f of d e minus e k minus e f. This term with the 2 inside, if you take the 2 inside here, this term is nothing else but volume integral g k f d e k minus e f d k. Okay. This is the density of states. So, the density of states which are available between k and k plus dk, the number of states which are available for occupying between k and k plus dk per unit volume of the sample into the occupancy of the state, which is given by the Fermi-Dirac distribution, that gives you the total number of particles in the system. So, this just comes out from here, that this is nothing else but this. So, g k, which is the density of states per unit volume, is 2 into 4 pi k square by 2 pi the whole cube, and g k d k is the number of states between k and k plus dk per unit volume of the sample. Now, the number of states, as you know, cannot change if the total number of states is always constant. So, whether I write it in terms of momentum or if I write it in terms of energy, Gk dk will be equal to G of E dE, where E is the energy of the particle, Ek is the energy of the particle. Whether I am counting states in terms of momentum or if I am counting states in terms of energy. So, I have states which I can label as E1, E2, E3, or I can label with them as K1, K2, K3. The density of such states, okay, or the total number of states between k and k plus dk is going to be the same whether I look at it and count it in terms of energy or if I count it in terms of momentum. So, I can equivalently write my density of states in terms of energy as G of k dk by dE, and this is the density of states which I can write in terms of energy of the particle. This is an alternative way to write the density of states. Instead of writing the density of states between k and k plus dk, G of Ek into d of Ek is the number of states between Ek and Ek plus dEk, and this is of course per unit volume of the sample. So, if I want to write down the total number of particles, again I can write it in terms of V into integral of Gk Fd Ek minus Ef dk, and I can also write it as V into Gek Ek minus Ef dEk. So, the total number of particles can now be expressed in terms of the density of states. Whether you write it in terms of energy or you write it in terms of momentum, the total number of particles is equal to the volume into the density of states which are available times the occupancy of those states integrated over the entire energy space. This will be 0 for energies which are greater than Ef, and it will be 1 for energies which are less than Ef, and G of Ek is related to the density of states in momentum space by this relation. And now we will calculate what is the expression for Gek, because this we know is 2 into 4 pi k square divided by 2 pi the whole cube, and Ek is h cross square by 2m k square. So, using these two expressions, we will calculate Gek, which is the density of states of at energy Ek.